a typical concentration versus time diagram. That concentration shows up on mine. For some reason, it's not showing up on the screen. But right here, we have concentration in molarity. And we're looking at changes in reactant and the two products. So our overall balanced equation here is 2NO2 yielding 2 nitrogen monoxides plus oxygen gas. So that's our overall balanced equation. And you'll see, I hope, by the time we're done, that our stoichiometry is reflected in these changes of concentrations. I hope that would be a little self-evident, but we want to make sure we note that. Let's take a look at some key aspects of this diagram. We are starting with 0.01 molar of our NO2, and we are beginning with none of our reactants, 0. So if we go watch our NO2 over time, watch your units, because sometimes time's in minutes and sometimes it's in seconds. It's decreasing. So reactants decrease with time in terms of their concentrations, logically again, I hope, and products increase. And so you see that increase here. And notice it's a curve. That can be somewhat problematic as we do our analysis. Not horrible, just adds a little nuance that we have to pay close attention to. And then the oxygen also increases with time. Well, a rate is the change in some sort of measurement. You know, we can change in distance, or in this case, change in our molarity per time. Or we may be dealing with partial pressures. So it could be the partial pressure changing with time. Well, that's pretty much a rise over a run, and that means that our rate is going to equal the slope of the line, which is lovely, except it's not a straight line, or not always a straight line. And that means that our rate is not a constant value. Our rate is changing. And so when we're discussing rates, we have to be very careful to specify how we are measuring those rates. And I'll show you that in just a second. I want to point out just two more things here. I want you to note, if you take any one point and measure it here, that the rate of formation of nitrogen monoxide is twice the rate of formation of oxygen. That's because for every 1 oxygen, I get 2 NOs. And you notice, I hope, a 1-to-1 correlation between the NO2 and the NO. Now, since concentrations are a loss, the rate for our reactant is going to be a negative value, and the rates for our products are going to be positive values. Now, the other thing I want us to note, and we'll talk about this the next unit, but eventually these level off. They stop changing over time. Now, they may stop when the products are higher reactants. When they stop, the reactants could be higher than products. There's a variety of ways that that can end, but eventually it appears as if this stops. So this here, where the rate appears to stop, is called a dynamic equilibrium. We saw that word equilibrium before. It's very hard to teach one without at least giving you a glimmer of the other. What has really happened here is that the rate of our forward becomes equal to the rate of our reverse. So for every NO2 that decomposes, we would have nitrogen monoxides and oxygens reforming the NO2. And so at the molecular level, if we could tag one of these maybe with an isotope or more likely a radioactive isotope, then we could trace it and we would find if, for instance, if it was the nitrogen, sometimes it would be in the product, sometimes it would be in the reactant. So on the molecular level out here, we still have changes. Okay, so that's when these level off. Now, we're going to set that aside for now and just focus on the beginning parts of this graph and define the way scientists or the point at which, not exactly the experimental manner with which they do it, but the points at which scientists measure their rates. So let's take a look at, whoa, crayons, get something pretty here. All right, so there's 3 ways that this is typically done, and you need to pay close attention as a scientist to how it's being measured, because you can't compare experiments directly if one is measured as one type of rate and the other is measured by one of the other 2. The first is called an initial rate. And what is done, I'm going to show you this graphically in a minute. We're going to make a tangent to the curve at time equals 0. That's why we call it the initial rate. So if we have a tangent of the curve, what we'll do is we'll take the slope of that line, and the slope of that line is the rise over the run, aka the rate. That's called an initial rate, and that will be the most common that you're going to come across. Now, the other is an instantaneous rate. So we as a scientist would define the point in the reaction that was most convenient. Maybe it provided us with the most accurate and precise data by picking a particular instant in the process. And so that's going to be at a defined time. And it's defined by whoever's performing the experiment. And again, we'll do a tangent to the curve, and we'll take the slope of that tangent, and the slope will give us the rate. Now, you need to be able to draw these and describe them in detail. This is all about learning to articulate your arguments and explain your knowledge. So pay very, very close attention to this. This is a key justification type of a question. Now, there's also an average rate. And in an average rate, we pick 2 points. And you can always make a line between 2 designated points. And we would get a straight line between those points. So point at time A to a point at time B, and we take, you guessed it, the slope of that line. Really, it's not a tangent at that point. That was poorly worded on my part, and that would be the rate. Okay, so that's the description in words. Let's see quickly how this plays out on a graph. So this is in your notes. And let me see if I can draw these. Fortunately, we have computers that can do tangents for us much more effectively than I can. But I want to at least give you an inkling of what we're going to do. So the first is we take a tangent to the curve at time equal to 0. So if I can kind of shift that a little bit, we take a tangent right at time equals 0. And then we would make our computer do this. We would take the slope of that tangent, and the slope of that tangent would equal our initial rate. So you'll see quite a bit of the data that we're going to analyze, and in the data, the column that has the rate data will say specifically it's the initial rate. Now, another would be to designate a particular time. So let's say the scientist said, okay, we're always going to measure the tangent at time equals 8 minutes. And so again, we take a tangent to the curve. Need a good math teacher to show me how to do this a little better, but I think you get the concept. You're not going to have to be doing this mathematically, where, man, if you get your tangent wrong, you're in big trouble. It's not like that at all, but you will need to be able to sketch it out. It's quite common because graphs are one of our models of explaining our knowledge, just like words or mathematics or pictures. And so you need to be able to lay out these lines, sketch out these lines, and explain how the rate is determined from that line. But you're not going to need to do it numerically. All right, now let's see what an average rate would be. Let's take an average between this 8 and this 40. So that's a little bit more straightforward because we can just connect the dots this time. So we take the slope of that line, and that would become our average rate. So we have our initial rate, we have an instantaneous rate, and in every case, the rate is determined by the slope of the line that is drawn through there. Now, we're going to do a few calculations of that, and let's take a look at those very quickly. This will be a longish video, but I think it'll keep everything together here. So let's take a look at the relationships between rates measured. We already saw that our stoichiometry came into play here. So in our reaction with 2NO2 yielding 2NO plus O2, in this case we have a loss, and we do 1 over 2. We take 1 over the coefficient times the change in either molarity or partial pressure for NO2. Let me erase that with a smaller eraser. Okay, so it'd be our molarity of NO2 over time is equal to, now this is a positive this time, we'd have 1 over 2 times the change in NO over time. And both of those are also equal to, so we could compare any two of the three of these. I'm going to be explicit here. Oxygen is 1 over, and we want it over its coefficient, which is an implied 1. And then we would take our delta molarity of our oxygen per time. So you'll see some web assigns on this as well. Now this here, this big long thing, that simply represents the rate of the reaction. And so we will be talking a little bit about comparing those rates, and I'll show you how we can streamline that a little bit. I was hoping to finish this concept, but it's really not going to be possible. So I'm going to go ahead and sign off now and I'll see you back on the next video where we will pick up this conversation